Well, at least his hair is protected. That's important. We're starting chapter 13.2, and we're going to begin with some vocabulary. You can see up here in Objective 3, you need to look out for these terms: somatic cell and gamete, autosome and sex chromosome. Then we're going to talk about the similarities and differences between haploid and diploid cells. And then finally, number 6 talks about 3 different life cycle patterns. I won't even explain now. You'll see in a moment what those mean. But first, the title of chapter 13.2 is Fertilization and Meiosis Alternate in Sexual Life Cycles. What this woman is looking at here are a bunch of chromosomes. And these chromosomes have been prepared. So here's how she did it. She took a cell from an organism. She killed the cell basically with a chemical so it wouldn't divide any longer or live any longer. She then stained the cell with a dye, and she then went all the way down to the nucleus. Maybe she took it out, or maybe she cut the cell in half, and she's now looking at the chromosomes that exist in the nucleus. And this can help scientists determine a lot of things about diseases or the health of a cell. This is a human somatic cell, and a somatic cell is any cell other than a sexual gamete cell, such as a sperm or an egg. Those are gametes, and somatic cells would be everything else, like a liver cell or a heart cell or a muscle cell or an ear cell, for instance. Those are somatic cells. They have 23 pairs of chromosomes. Where did these chromosomes come from? Well, one set from your mom, one set from your dad, and when put together, it equals 46 chromosomes. So for instance, in any cell from me, let's say we took a cell from my kidney, it would have 46 chromosomes, 23 from my mom, 23 from my dad. These 23 sets of chromosomes consist of 22 autosomes, which are also, you can call those somatic cells. They're the non-sex cells, and a single sex chromosome. You can see that you can arrange them in pairs here. I told you earlier that it's important that the genes are on the same spot on everyone's chromosome, and this is why, so that when my chromosome 11 matches up with my wife's chromosome 11 and we try to make a baby, that the information is exactly the same and in the same place on our chromosome 11s, say with the ability for my daughter's heart to be created in the right way, for instance. What you see here, this is a misleading figure. I dislike this because these chromosomes are X's, and that only happens right before mitosis, after the S phase of anaphase. I wish these were just single lines here on the left, which they kind of look like they are on the right side here. This is called a karyotype. And again, researchers like that woman in the other picture can do this on purpose to identify if there's any trouble with the cell, for instance. The homologous pairs of chromosomes, or homologous chromosomes, are these matched up chromosomes. Like, for instance, in my cells, I'm going to have a chromosome 1 from my mom, chromosome 1 from my dad. Those are called homologous chromosomes. We've already talked about this point. Answer this. Well, I've already talked about this, 2 sets of 23, and you can see here this is represented by 2N. 2N means 2 sets of chromosomes, and in a bullfrog it looks like there's 26 total chromosomes in every bullfrog cell. That means that from the bullfrog's mom and from the bullfrog's dad, it each got 13 chromosomes, which have come together now to make 26. This is called the diploid number. Here's what's a little bit different, is that a gamete, which is a sperm or an egg, has to have a haploid number so that when they come together, the correct diploid number is there in every cell of every organism, starting with the very first cell that's made. Way over here, we'll call that the zygote. And this haploid is it's signified by this lowercase n. At sexual maturity, your ovaries and a guy's testes will produce haploid gametes, and they're produced by this process called meiosis, not mitosis. And meiosis is very different than mitosis, and we'll get into the details here. Additionally, it results in 1 set of chromosomes in each gamete. it's kind of a mixture. So for instance, when I make a chromosome 11 to pass along to my daughter, my chromosome 11 came from a chromosome 11 from both of my parents. They got kind of mixed up. It's not straight from my mom, straight from my dad, or an equal mixture from each that creates my single chromosome 11 that's in my sperm created by my testicle by meiosis. It's kind of a mixture of the two. We'll get into how that happens. So answer this question: what's the haploid number of this cell down here, and is it a set? Is a set of chromosomes haploid or diploid? We'll take a look at this tomorrow. So here's a privet shrub. This is a shrub that grows all throughout the United States. And here's a human, and we have the same diploid number of 46 chromosomes in each of our cells. Now, who's more intelligent? Well, the privet shrub gets fed and watered, and it doesn't have to do anything. Okay, I'm kidding. Answer this question. Privet shrubs and humans each have a diploid number of 46 chromosomes per cell. Why are the two species so dissimilar? Press pause and try to answer this question, please. Here's a duck-billed platypus. His diploid number is even more than ours, 52. Here's a field horsetail, which has a diploid number of 216. Now, are you smarter than a field horsetail? Maybe you are, maybe you aren't. But the point I'm trying to make here is that there doesn't seem to be a correlation between number of chromosomes and intelligence of organisms. Here's the great example that science likes to give. This little flower called an adder's tongue. Its diploid number is 1,266 chromosomes per cell. That's a lot of chromosomes per cell. So, glean from that what you will. The last segment of chapter 13.2 talks about the variety of sexual life cycles. What this is a picture of is this is a picture of a human. This may not look like a human up here, but it really is once the sperm has fertilized an egg. I want you to realize that at one time you were in your mother's uterus a sperm that had gotten into an egg. That's what you were. You were a single cell, and then we'll call that fertilization. And then that fertilized egg began to divide by mitosis, and you see that here. And now here you are, this big person, either a man or a woman, and in your testicle or ovary, you are undergoing meiosis to create your own sperm or egg. And so this, your book likes to make this stretch. This is the life cycle of a human here, and it's called alternation of generations. There's a gametophytic or gamete-rich part of the generation of the human up here, and then a sporophytic. You're going to see those two terms. A sporophytic phase of human development down here. So it's common to all organisms that reproduce sexually. You're going to see a higher organism like a field mouse here or a human. You're going to see that we spend most of our time down in the diploid or sporophytic state, and less of our time as a higher organism in this gametophytic or haploid state. Higher organisms spend more time as diploid organisms, and you've spent more of your life as a diploid organism than you have as a fertilized egg, basically, or sorry, as a sperm and an egg. And so here's the translation that we're trying to make, is that plants also have alternation of generations, but you can see here that they have more time relative to humans or higher organisms that are multicellular eukaryotes. They have more time as gametophytes or gametes than we do, and it's about 50-50, it looks like, as far as the diploid and haploid stages of their life cycles go. And you're going to see here, finally, a fungi and some protists, these lower organisms. They're multicellular, but they're going to spend even more of their life cycle in the gamete phase. Make sure you try to answer this question. Fertilization is to a zygote as meiosis is to which of the following? And spend some time answering these objectives, and we'll talk about them in class tomorrow. Thank you for your attention.